The equations, the chemical reactions we just looked at only had gases in them, but lots of reactions involve pure solids or pure liquids or solutions. So let's think about pure solids and pure liquids. Here we have an equilibrium, carbon monoxide in equilibrium with carbon dioxide and carbon. So here, excuse me, here we have an equilibrium with a small amount of solid carbon in the container. Here we have with a large amount of solid carbon in the container. What we'll find is that the concentrations of CO2 and CO in each of these containers, if the containers are at the same temperature, the concentrations will be the same. Does having more carbon in here change the equilibrium? No, it doesn't. What is the concentration in moles per liter of solid carbon? You could figure that out using the density. Density is mass per volume, right? So you could say, well, let's take 1 liter. What's the mass of 1 liter of carbon? And then use the molar mass to find the moles in that, right? So the concentration of this solid would be calculated from the density. Is the density of this sample different than the density of that sample? No. Density is an intrinsic property of a substance. Density doesn't change based on how much you have, right? It's the same. When some of this carbon, let's go to the big one. If some of this carbon reacts and we end up with a smaller lump, has the concentration of carbon changed? No. As long as there is a little bit of solid carbon in here, the equilibrium is going to be the same. Doesn't matter how much there is. So the concentration of the solid doesn't change, and so it does not affect the equilibrium. So it is not included in the equilibrium constant. The same is true for pure liquids. You can calculate the molarity of water. Water is about 55 moles per liter, pure water. Well, it doesn't matter how much water you have, it's always 55 moles per liter, right? So just like the solid here, as long as there is some present, we're not going to have it affect the equilibrium, so it doesn't get included in the expression. What about a solution? Can the concentration of a solution change? Well, yeah. That's where we're most familiar with molarity is, defining aqueous solution concentrations. So solids and liquids do not get included, but gases and aqueous things do. Okay, so let's practice. Write the equilibrium expression for the reaction between carbon dioxide and water. So we've essentially added one thing to what we learned last week. So equilibrium constant, and they're not specifying pressure or concentration. If it was all gases, we could do either, but if it's not all gases, Kp doesn't mean anything. So Kc is the default. So what's the expression for Kc for this? Well, we take the products, right, their concentrations, raised to the coefficient. Are these solids or liquids? No, they're aqueous. It's dissolved in water, but it's a solution, and solution concentrations change. And that's going to be divided by the concentration of CO2. That's a gas. The concentration of a gas can change. You can squish it together or let it expand. Do we want to put H2O liquid in the denominator? No, because this does not change. It's always going to be 55. So we just leave it out. So this is a little bit like writing net ionic equations. So you've got your molecular equation. Anything that is a solid, a gas, or a liquid, a pure substance, you just copy the formula down. You don't split it into ions. You only split into ions things that are aqueous, right? So it's where you're choosing what to include based on the state. So we're including different things here. Here we're including gases and aqueous solutions. These are the things whose concentrations can change. Liquids and solids, concentrations can't change. Any questions? On exam 2, there will be a question, something like this, intended to see if you remember that. And so, this would be the correct answer, but this answer would also be there just to see, right? So you could say, well, you're trying to trick us. Well, if I tell you about it, is that trying to trick you? I don't think so. I'm warning you. Watch out for that, because I'm going to do it. Okay? Okay, write an equilibrium expression for this chemical equation. Okay, so I'm going to give you a minute to do this on your own. Okay, what'd you come up with? Kc is equal to the concentration of CO2. That seem too simple? Well, this reactant and this product are solids. When the equilibrium is establishing itself, those concentrations do not change. So if I throw more calcium carbonate into the reaction, it doesn't affect the equilibrium. If I throw more carbon dioxide in there or take some out, if I change this, it will cause the equilibrium to shift. So the equilibrium constant here only depends on the CO2 concentration. Any questions? So I was talking to a student before class, and they took the exam yesterday, and they were a little frustrated with themselves. I listen in class, and it all makes sense, but then when I tried to do the problems on the exam, I got them wrong. Okay, so I'm going to tell you a story. So I grew up in the Midwest, and I went to Iowa State University for my undergrad. And what they would do there when they built new buildings, because gradually all the green space is disappearing, but they'd have this big green lawn, and instead of putting in sidewalks right away, they would wait like a semester or two, because people would walk through the grass, right? And in Iowa, we call what happens a cow path, because people walk the same way, the grass dies, right? And you get a trail, right? We call those cow paths, because that's what cows do in the pasture. Cows are coming in, their cows actually got to go into a pasture, not like the cows in Tulare. But they would, come in for milking, and they would tend to follow the same path every day, and so they'd make this trail, right? So after those student cow paths were established, then they would put the sidewalks there. And they didn't have trouble with students making trails on the grass, because they had put the sidewalks where the students were going to walk anyway. Genius, right? What does that have to do with learning chemistry? So hearing this in class and it making sense and you understanding it, that's like walking through the grass once. Nice fresh grass. Can you see where someone walked? Yeah, you probably can if it's kind of long, right? If it's super, super short, you can't. But if there's dew, you would at least see footprints, because the dew would get messed up. But you might see, think about going through a meadow with long grass. you could see, at least for a while, where someone had walked because the grass is bent, right? But then it's going to recover. So that's like your brain. So lecture is you walking through the grass once. It makes sort of an imprint there, but if you don't do anything else, it's just going to fill back in, and you're like, it never happened, right? So what you need to do is you need to practice it, right? You need to do homework problems. You need to review notes. You need to think about it. And every time you do that, you're walking the path one more time. And it doesn't take too many, people walking through there to make a cow path, right? But you have to make some cow paths in your brains. Okay, end of story. Let's look at this one, right? An equilibrium expression for this chemical equation. And here they are specifying that they want Kc so what goes on the numerator? Cl2 squared. See, now we're walking down that path another time. Why don't we have H2O in there? It's a liquid, its concentration doesn't change. We leave that out. It's great to remember why, but if you can just remember, because she said so, that's good enough. And then what goes in the denominator? HCl to what power? Fourth, and O2 to the first power.
So if it was all gas, we can use Kp.
If it was all gas, we could use Kp. And for this one, we could use Kp because the liquid doesn't show up in there anyway. So we could have the partial pressure of Cl2 and the partial pressure of HCl and the partial pressure of O2. And that's why they specified Kc. Any questions? Which one do you use in a given problem? Well, sometimes it's going to tell you which one. Other times, like if they're giving you some pressures and asking you what the equilibrium constant is, well, they probably mean for you to use the pressure one because that's what they gave you. If they give you concentrations, most likely you're going to use the concentration one. For which of these reactions does Kp equal Kc? What are we looking for? Equal moles of gases, right? So this first one, do we care about how many moles of solid there are? No. Here's another solid. Do we care? No. Ignore those. Are the moles of gases equal? No, they're not. So it's not that one. What about this one? Yeah, we leave the solids out. We've got 3 moles of gas here, 3 moles of gas there. Let's just check that last one. Equal moles of gas? No. We've got gas products, but no gas reactants. Kp equals Kc when the moles of gas reactants equals the moles of gas products. The reason for that is that all the 1 over RTs are going to cancel out. If it's not an equal number of moles of gases, then they're not going to cancel out, and we have to include that.